In this video lesson, we're going to take a look at electrochemical cells. So we'll look at Voltaic cells and electrochemical cells. So a Voltaic cell uses redox reactions to produce an electric current. They're also known as batteries or galvanic cells. So we can see an example of one right here. We have two half cells and a salt bridge and a voltmeter. We're going to take a look at how these work very shortly. So the components of a voltaic cell, they're made of two half cells. In this example, we have our zinc electrode, so that's our anode, in the solution of zinc sulfate, and a copper electrode, or the cathode, in a solution of copper sulfate over here. We also have a salt bridge to allow ions to flow to complete the circuit and to prevent the buildup of electric charges. So in these reactions, we have electrons moving through the electrodes and through the circuit, and the ions move through the salt bridge. So at the anode, when we put the zinc electrode into the zinc sulfate, the zinc gets oxidized. So the zinc releases electrons into the solution to become zinc 2+. And then the zinc 2+ ions in solution are reduced to become zinc. So the half reaction looks like this. So zinc becomes zinc 2+ plus 2 electrons. And that's shown with an equilibrium reaction, so it can go both ways. When the copper electrode is placed into the copper sulfate solution, the copper 2 sulfate, the copper is less likely to lose electrons. So in this case, the equilibrium will lie to the right because there'll be less chance of the electrons being released. So it'll favor the right side of not releasing the ions into solution from the copper cathode. So a salt bridge is often just some filter paper soaked in potassium nitrate or any salt solution. The negative ions will flow from the salt bridge to the anode, and the positive ions will flow from the salt bridge to the cathode, and that prevents a buildup of charges in the cell. So in a voltaic cell, the more reactive metal drives the direction of the reaction. So because the zinc is more reactive, it will become oxidized and the copper will be reduced. So that will cause a potential difference between the half cells, and that is called the electromotive force, or the EMF, or cell potential, which we'll talk about in greater detail in a further lesson. So you can see in this solution, the copper or the zinc ions are leaving the anode, and the copper 2+ ions are forming on the cathode. So the potential difference for different voltaic cells depends on a few things. One, the electrodes and the ions that are involved. So the further apart the electrodes are from one another on the metal activity series will have an impact. The temperature of the solution has an impact, as the temperature of solutions always do, and the concentration of the ions in the solution will also have an impact. So this is just a sample of some cell potentials. I believe these ones are taken from 1 molar solutions of the different metals. So if you look at copper and magnesium, the cell potential is 2.71 volts. Copper and zinc is 1.10 volts. Copper and iron, 0.79. Lead and zinc is 0.63. Lead and iron is 0.32. So you can see that there's a variety here. But one thing to note is the further apart the metals are on the activity series, the greater the voltage will be generated. So a cell diagram convention is just a shorthand way to draw a voltaic cell. So you draw the anode and the cathode, and then a double parallel line to show the salt bridge. And then there's a line between the metal and the ion to show the phase boundary as well. And then you have your anode and your cathode. Here's the instructions on how to draw them. So a single vertical line to show a phase boundary between a solid and an aqueous solution. So right here, this is our phase boundary between the zinc anode and the zinc ions that are in solution. So there's our anode, zinc and zinc 2+. Then our cathode is copper 2+ and copper with that phase boundary again. So the anode is on the left and the cathode is on the right. And then you put your double line for your salt bridge. If there's two different types of ions in the same half cell, you'll just separate them with a comma. So sometimes you might have more than one ion type in there, but you don't include spectator ions. So if it was like a solution of zinc nitrate, you don't include the nitrate. And if it was copper nitrate, same thing. You don't include the spectator ions.